Hey, g'day, it's Prezzo. Thanks for joining me in the workshop today. Now, this is episode 2 of building the Titan 60 model aircraft engine. And I must say, in the last episode where I introduced the engine and talked about the original designer and did some of the machining, I was totally blown away by the response. Now, it seems like a lot of people have fond memories of aero modeling when they were a youngster, and certainly that was a big part of my upbringing. A group of friends and I would head off to the local park with a finely crafted scale model or scratch-built aircraft, all in balsa wood, and we would return in the afternoon with a pile of balsa scrap. But that was all part of the fun, and I think sometimes building the aircraft is almost as much fun as flying them. Now, in the last episode I machined the crankshaft. I held over one operation which was a bit awkward, and we're going to look at that first up today, and we're going to have a go at machining the casting for the crankcase. And we can do about 2/3 of the operations on that. There's a few that will need to be held over till later, like machining the venturi and drilling the cross hole for the spray bar, and also extending the drilled hole for the venturi down into the crankshaft. So that's all going to come at a later stage. But first, let's head over to the bench and look at the drawings that I came up with for machining these odd parts on the crankshaft. Okay, our first job today in making this crankshaft is to mill these two flat areas on the crank disc. Now, the reason they are there is to balance out the rotating mass of the crank pin. So that's a fairly significant chunk of metal that's offset toward one side of the center line of the crank disc. And we balance it out by subtracting some weight on this side and adding some weight here. Now, this weight that's been added is really just an extra thickness on one side of the center line. Now, this is a 2D CAD drawing that I made from a 3D solid model, and I did that in Autodesk Inventor. And I was able to generate this geometry quite easily by looking at the original drawings. There was enough information there in order to work out where everything went and create that 3D model. So let's have a look at the original drawings. You can see here that there are 4 points that are required to be able to work out the geometry of those angular cuts. So at the top there's a point either side of center, either side of 12 o'clock, and that's 1/4 of an inch either side. And at the bottom it's at basically the 3 o'clock and the 9 o'clock position around that circular end. Now, that's fine if all you're doing is actually recreating this as a drawing, but when you go to machine the part on the milling machine, that's really not the information you want. So let's have a look at what I dimension on my other drawing. And what I was interested in is, what is that angle? Now, it works out to be some weird angle. It's 124.83 degrees. And that's really not very useful for me when I go to set this up on the milling machine. So I thought about this and I thought, well, what I'll do is I'll just simply mark out all of those points by bluing up the end of the crank disc and then trying to work out where those positions are. So I've got 2 scribe lines at the top here, either side of center, and I've got some scribe lines on the back, and I've sort of joined it up with the scribe line. But even then, that's not really very useful. It sort of allows you to eyeball this part in the vise, and you may or may not get it right. It really then depends on how good your eyes are as to how level you can get that scratch mark and whether you're going to be able to hit that with the milling cutter on the way down. So I thought about it and I thought there's got to be a better way, and I said to myself, now what would Joe Piezinski do? He certainly wouldn't do it this way. So let me show you what I came up with. So here's a slightly larger scale drawing. This is drawn at 2:1, and these are the areas that we need to remove. So just this little sector here and here. And in the notes it says you can grip this in a milling vise to be able to do this process. So the area we'd be gripping to do this is just down here. So it's not a lot, but it's enough. And what I was interested in is, how can I arrange this so that the angular surface we need to cut is going to be parallel to the vise jaw. So if you can imagine, this is the vise jaw here. And what would be the distance from the top of the vise jaw to the tangent point on the crank pin itself? So what I've done in my CAD program is I've created a new assembly. I made up a mock vise jaw, and then I oriented the end of the crank disc so that the surface we need to machine is parallel to the jaw. Now this gives me two things. It gives me the distance I need to machine from the top surface of the crank disc down to that angular surface. It works out at 3.27 millimeters or 129 thou. And it also gives me the distance between the top of the vice jaw here and the tangent point at the crank pin. And that works out to be 8.72 or 343 thou. So all in all, much easier to set up. So really all I need to do now is to use an adjustable parallel set to that dimension, 8.72, and slide that underneath the crank pin and on top of the vice jaw. Clamp it, touch off with my milling cutter right at the very tangent point at the top there, and then machine down in Z, 3.27 millimeters, and I'll have my surface. And then of course you just flip the whole thing and do that a second time. So all in all, it takes all the guesswork out of it. You don't have to worry about looking at scribe lines or trying to scribe lines in the first place. You sort of eliminate all of that, and we've got a very repeatable setup that we can do. Over here on the middle, you can sort of see how this has to work. I've got to be able to grip this crank disc by the thickest section just here, and there's not a lot of that in the vise itself. So I've got 2 pieces of paper, and that just helps to take out any irregularities in that surface and make sure we've got a really good grip. And all we need to do then is to make sure that the crank shaft is resting on the fixed jaw of the vise. So we just sort of roll it over, make sure it's sort of rolling on the outer surface of the crank shaft. And then I've got an adjustable parallel which has been preset to the dimension shown in the drawing. And that's going to go on the moving jaw. Make sure that we're not sort of sitting on this corner of the adjustable parallel here. That's all good. And then we just roll the crank pin down until it's resting on the adjustable parallel and snug up the vise. Then we're just going to touch off on the top surface of the crank disc, and then we can machine down to the dimension shown in the drawing. Now I did have to amend that dimension. So the theoretical dimension was going to be 3.27 millimeters. I've amended that to 3.18 because when I made the crank disc, I had to clean up the surface. It wasn't, it was just like the mill finish, and in order to get a smooth finish on that, I'd take a couple of hundredths off that, so that's why that discrepancy is there. And looking at the drawing now, I'm thinking that the original designer just simply decided they were going to machine down 1/8 of an inch, or here it's shown as 0.129, should be 0.125, but that's what it looks like. So that would have been a more sensible dimension to show on the drawing. However, I'll get this all ready, and then we'll machine the 2 cuts. And the most important thing here is that what we end up with is symmetrical. Whether it's precisely the same as the original drawing is not so important, but does need to be symmetrical. Now, that took a bit, but I got it. That's firm. Just gave that a quick deburr and it's come out looking pretty good. And I did check the dimension across these corners here, and on the drawing it's shown it's 1/2 inch, but it's a very awkward thing to measure with that angular face coming off the two sharp edges there. And that's precisely why I didn't want to do it that way when I was setting it up in the mill. There are a couple of minor operations still to be done, like drilling a cross hole here for the engagement of the prop driver. That can wait till later. So I'm going to put this in the parts box now and move forward with the crankcase. This is a close-up view of our crankcase casting. Now this is made of a material called Tenzalloy, and also sometimes called aluminium 713. It's a zinc aluminium alloy, and it's supposed to machine really well and leave a good surface finish. Now all I've done in preparation for machining is just to file off those flash lines. They were actually really good, just need a little tiny touch with the file here and there. And then after all the machining is done, I will sandblast this. Now it's a bit of a risk sandblasting it later because you don't want to get any grit inside the engine, but I can plug all of the holes in the openings and then I'll give it a light sandblast on the outside. Now some people might do this now before they do the machining, but I've got to grip it by this section of the engine here and it will almost certainly leave marks in it. So it's better to get them out later and then do the sandblasting. So it turns out I can put this in my smaller 3-jaw chuck, and the venturi fits between these jaws, so I can grip it a bit further back. And with my larger chuck I can't do that, so that holds that quite securely. And the notes say just to check the alignment, and at this stage that looks pretty good. And what we need to do now is machine off this back face here until these 4 lugs are flat, and then we're going to bore out the opening in the crankcase. Now it's a bit of a risk when you're machining castings because you have to clean up both ends, and the amount that you take off both ends will influence other features in the part. So for example, the bore where the piston will fit still has to be in the correct place relative to this back face here. If I machine too much off this face now, it potentially changes the position of the bore relative to that face, and therefore relative to the crank shaft and the crank pin. So you've got to be a little bit careful and try and estimate how much material you can take off either end. Now the notes aren't very specific, it just says to clean this up until these lugs are flat, so that's what I'll do. Just turning this by hand, just seeing how the tool tip tracks around this circular boss here, and without doing any adjustment at all it looks pretty good. So I'll go ahead and clean that up now. Still got a bit to come off, so these lugs are flush with that surface there. Alright, this isn't going to work. I'm actually hitting the tool holder on this part of the casting here, so I'm going to have to change out to a different tool. That does machine nice. Now we need to bore out this opening here. It's where the crank disc will fit. Now our build notes say now that we need to open up this back face of the crankcase, and we've got to machine to depth and also to diameter, and I've got a boring bar set up to do that. Now I've just checked, and at the back face of this opening here we've still got 3mm of material to come off in length. So what I'll do is clean up that face there first, very, very close to our finished size. Then we can sort of roughly bore all of this. Then we need to bore through here for the crankshaft bush. So at this stage, you know, like any of these operations, you're basically just roughing out. Better to do it that way and get clearance, you know, so that you're not sort of running a tool like a boring bar into raw stock at the end of this cavity here unexpectedly. So you know, sort of you need to know where all these surfaces are because you're sort of machining blind. So at 30.5 millimeters deep, I'm actually cutting material off the back wall of that opening there. So I'm going to set that as my limit, and then I'm going to clean up this surface here, the actual bore, and then just sort of work back from that. Alright, we're at 32.39 and the bore is shown there as being 38 and change, so still got a fair way to go. Always worth checking though. Okay, so I've got a full diameter inside there now, so I'm going to get some measurements and start working out my limits on where I want to go at this point. I don't want to machine any of this to finished size just yet until we've done the bore for the crankshaft sleeve. So what I normally do here is I'll set my caliper to the dimension that I want and then zero it, take a measurement, and that'll give me the amount still to go. So set that to 38 and we'll zero there. And the finished dimension is 38.35, so once I get to 38 I'll stop there. So I've got 4.27 still to go, and I'm going to set that on the DRO and we'll just keep boring out until we get to that dimension. So just off camera I've machined the back face of that bore close to size, and you can't see it anyway, so I just did that, and I'm almost to diameter on the bore itself. So what I need to do now is to bore the remainder of the casting, and that means getting a lot of stick out on my boring tool and trying to get that at least with parallel walls and close to size, and the reamer will do the rest. But that's just a cord hole inside this section here, and it's not running true. If I try and run a drill bit down there, it'll pull it off center, and then the reamer will do the same. So the reamer has to follow at least a concentric hole, even if it's slightly bell-mouthed or slightly tapered, but it has to be concentric with the main bore here. That's cutting okay, but I've got to be careful here. This section here, the exhaust manifold, is going to hit the tool block before we hit the back of the crankcase. So, yeah, it's a bit scary. I think I'm just going to hand feed this. Yeah, alright. Wish me luck. Alright, off camera I bored out the front section of this casting as much as I can. It's still a bit undersized. And I've just realised that the reamer that I bought for doing this job is actually for the inside of the bush, the crankshaft bush. So this is 9/16. The one that I need for this hole is 11/16, and I don't have one. But I have got an adjustable reamer. So what I'm going to do is with the boring bar, I'll bring this out almost to the correct size, leaving a little bit of material to take out with the reamer later. And then I can set up the adjustable reamer and keep taking that through, and I'll have I'll have the bush made, and I can use that to check my sizing as I go, or I might make up a go, no-go type gauge. But unfortunately, yeah, big imperial reamers don't have a lot of them. Now she went ahead and did all the rest of the machining inside this bore here off camera because you can't see it anyway. And I'm just going to check this diameter here now. That was the last cut that I did. It's showing 200ths under, 100th, so it's less than a thou. And then I had a couple of thou either side of the actual dimension called out in the drawing, so I'm saying that's good. I'm going to chamfer this edge here now. I can't get at the one right inside there, it's too deep, so I'll do that with a countersink tool just to break the edge. And then we're going to flip this over and machine the front off. And we'll do that on a mandrel. Sweet. This finish on this stuff is really nice. Okay, let's take it out. So there's a look inside, looking really clean and nice. And you can see at this end I didn't quite get it. I'm just like the last half a millimeter didn't quite cut through, but that's okay because when I trim the front of this now, that'll give me a smooth bore all the way through. Just put a bit of mild steel in the chuck here, and I've machined this down to be the same diameter as, well, the bore inside the casting here. And I put a very, very slight taper on that so that I can get it on nearly all the way. And I was going to give that a tap. And normally I would lock that with some super glue or Loctite. But given that we've only got to take a very small amount of material off the front here, that's still rotating. Alright, I think that's good enough. I can use a bit of heat to get that off, but we're just going to machine this back now to the correct length. And you can see there how close I was when I was trying to bore out that inside. So let's check this. Alright, I got it. Oh, got exactly a millimeter to come off. Alright, I think I fluked that. I'm not going to push my luck. So I'm just going to chamfer that now. So there you go, no super glue required. Okay, next thing is we've got to set this up and machine out the bore for the cylinder liner. Okay, we're at a fairly critical stage in machining this casting now, and what we have to do is to machine this bore, which will take the cylinder liner at a later stage. A couple of important things we need to do. We need to get that bore, this bore for the cylinder liner, aligned with this cavity in the back of the casting here, and therefore in line with the center line of the crankshaft. And we also need to make sure that the casting is more or less standing up vertical in the vise. Now obviously if I rotate this casting to the right, then this section here, which is the exhaust manifold, will be higher, and if I roll it the other way, it'll go lower. So we don't want that. We need to make sure that this alignment is correct. And when it goes in the vise and I've clamped that up, I've got no way of indicating this bore here. So I don't know how I am supposed to check to make sure my two bores are in line. So what I've done is I've made up a piece of PVC. Now this is a tight fit in the bore for the crankshaft, and it allows me to indicate on both sides of that piece of PVC stock. Now aluminium would be better, or steel maybe, but I think this is dense enough to do the job. And I've also relieved the top of that piece of PVC so that when I start boring down from the vertical section here, I'm not going to hit the PVC and sort of kick it offline. And what we need to do now is to make sure that we can grip this in the vise. Now I put just a Sharpie mark on the back of that bit of PVC so I can roughly align it. And and that aligns the cavity on the inside there as well. So we're going to put that in the vise. Now I've got a piece of brass bar in the bottom of the vise, and this PVC section is going to roll on that. And I've also got my vise stop set up here as well. So if I push that in against the stop and then tighten this up, what I can do now is indicate off both sides of that bit of PVC and get my alignment, get my center alignment, and then I can indicate off the end of that PVC and get my offset to the center of the bore. Now I've already measured all of this, so I've got all my measurements written down here, so I know the offset from this back face, that PVC stop. So when I come across here, I'm in the correct position. And then of course the other thing is, how do we get this manifold aligned? Now if I put a square on there, there's no guarantee that this part of the casting here is actually accurate. So I don't think it's any good to do that. I've got an alternate method and I'll show you that in a minute, but let's get all this indicated in and then we'll see if we're even close. I've got everything sort of snugged up here in the vise now, and I've sort of eyeballed that casting to try and get it vertical, and I've got one of these ball type edge finders, and that's because I can reach down into the vise here with that, and I've set the distance from the top of that PVC to roughly half its diameter. Now I'm going to be using the half function on my DRO, so even if I'm not exactly on center, it shouldn't make any difference. So let's go ahead and indicate this edge. Okay, let's do that 3 times to be sure. The other thing here is you can just lift up out of the way there and then go across to the other edge. Okay, we'll do this side. Alright, so I'm going to do the half thing on the DRO. Alright, that puts us on the center of that PVC. Now we're going to pick up this back face here and then move across to our center of the bore. So I've got my DRO zeroed now in Y, and we can offset this distance here. So 39.237 should put us exactly on the center line of the bore. Alright, next trick is to try to get the top of this casting level, and of course it's not level because there's draft on the casting. So this is the high point in the center, and then it falls away on either side, so you really can't run an indicator across that. The only way I can come up with is it's a Joe Pazinski trick, so I'll show you that. Okay, what I've got here is just a piece of composite plastic. It's sitting on an arbor, and I've turned the diameter of that piece of plastic to be the same distance or the same diameter as the distance from this edge of the casting to this sharp edge of the casting here. So I just measured that with calipers, got it as close as I could, and I've machined that stock to be the same diameter. So what I can do now is put this up into the spindle of the mill, lower this down, and then visually align those 2 edges to that piece of stock. The camera is now basically in front of the milling machine where I would be, and what we can do is lower that piece of material down and put it on top of the casting, and then I can see from where I'm standing now that this edge here isn't aligned with that piece of stock. So what I'm going to do now is loosen the vise. We can roll the casting left and right, and this is where this stop comes into play. So as I do that, I want to make sure that it's still rotating against that stop, so we're not actually physically shifting the casting left and right in X. That's really important because I went to all the trouble to align everything off that piece of material, that piece of PVC. So let's just gently loosen the vise. Okay, now without moving it laterally, we're just rotating it. Bring it back down. Okay, a little bit further. Alright, now I can feel that that's exactly right on that edge there. Should be right on that side there. Wait till I come around and have a look. Yep, that's good there. So now I can lock everything off, and we can go ahead and we can take the top off the casting, bring it down to its correct height, and that dimension will have to come off this piece of material here as well. And then we can bore that out and everything should be in line. And did I mention that apparently this is the last casting in existence for this Titan engine? So like, no pressure, right? If I screw it up, that's the last one in existence. So that's why I'm being so careful with this. Okay, I just turned the power feed off before we got all the way to the bottom. I just fed it the rest of the way by hand just to make sure I wasn't going to hit anything nasty at the bottom there. That all looks good. So let's get a full diameter on the bore now, and then we can start measuring. Alright, I'm going to have a proper look in there. I'm going to have to stick my head in the way, so I'm going to go off camera for a minute. Alright, I just had a proper look in there. I've got a full cut all the way around the top of the bore there now. Looks centered, so I'm sort of happy about that. At the moment I'm 2.5 millimeters undersized, and I've just been using one of these telescopic bore gauges to measure that. So I'm going to work up slowly to our finished dimension, which is 1.062 of an inch. And the part that fits in there is not made yet, so if I mess this up, go a bit over or under, I can make the other part to suit. I don't think that dimension is terribly critical, but let's try and hit it. And the only thing I'm finding is that the chips are packing in the bottom here. There's nowhere for them to go, so I've got to keep clearing that with air. Alright, this should be our last cut, and then we can take the top off this. I don't know about you, but I find these things really hard to use. Probably time to invest in a nice internal mic, I think. So I'm still getting about 500ths under size. Yeah, I'm thinking 500, so I'll do one more cut, but I won't show you that. Okay, we're about to do the top of the cylinder casting. I just swapped out for a 12mm end mill here, and we're just going to touch off here. Alright, going to zero the DRO at that point. And we've got to come up now a total of 32.97. That'll be the top of our cylinder, and we'll just trim that off there. Well, that's what I was hoping to see. So let's take this out now and have a closer look. Well, here's our two components done at this stage. Now, the crankcase casting is not finished. We still have to machine out the exhaust port, and we need to machine the opening for the venturi. This particular procedure has to happen later, after we've made the bush, or the bearing if you like, that fits through the crankcase. But I will be doing the exhaust port next and get that out of the way. Pretty straightforward, it's just like a straight milling operation here and facing off that face of the casting. There's also some drilling at the back here and so on, just sundry items that need to be attended to. But at this point I'm happy with the way this has turned out. And as you can see, the crankshaft fits through that bore. We don't have the bush in there yet, so it's going to look a bit sloppy. But that's how that works. And I've also purchased a 12-inch by 6-inch pitch prop, wooden prop, and I've already reamed this out to fit over the shaft there. And it's got beautifully sharp razor edges on the trailing edge there, and of course when you hand start these engines you've got to run your fingers across that trailing edge there. And there's always a potential for the opposing blade to come around and whack you on the back of the knuckles. So I've sort of grown attached to my fingers, but well, you know, it's all part of the fun, isn't it? You know, burnt fingers, cut fingers, yeah, it's all good. So here's the material we'll be using to make the bush. Now this is a sort of bronze. It's got a certain amount of tin in it, so it's not brass, and it's supposedly the correct material for doing this job. So we're going to machine that next, and we'll do a trial fit and see how that goes. So yeah, it's all going well to this point. Now, just in closing, because I think I've used up my half-hour limit on this video, but I must thank a gentleman named John Rist. He got in touch with me this morning, and he has linked to this video playlist on a website called Stunt Hanger. And that could have something to do with the amazing reaction I've had to the first video. I picked up about, I don't know, nearly 40,000 views on the first video, which is almost unheard of on my channel, and also a significant number of new viewers. So thank you so much, John, and thank you to the people who joined just recently. I do hope you enjoy this series. It certainly generated a lot of interest, and who knew? Apparently so many people have fond memories of working with model aircraft when they were young. So yeah, hang around for the rest of the series. I mean, even if it doesn't run, it's going to look fantastic, but the goal that I have is to see this thing run. It's never going to fly in an aircraft, but it just would be nice to see a few pops and a few splutters coming out of it. So that's all from me today. Thanks for being with me, and I'll see you on the next video. It's Prezzo signing out. Cheers.